Hello everyone. Today we're going to be talking about hypothesis testing and beginning chapter 9, and these are going to be the only slides for chapter 9. Taco Bell had a prototype in 2002 called Defy. This is in Minnesota somewhere. Taco Bell's two-story neon purple lit Defy arrived with a bold objective to get customers through the drive-thru in 2 minutes or less. The question is, how do you know if this is achieved? You take samples of wait times and service times, but how can you be confident that wasn't just a fluke? Well, that's an example of a hypothesis test. What is hypothesis testing? It's a sophisticated approach to verifying or rejecting claims about a property of a population. The claim about that property is a hypothesis, and we're able to verify the validity of a claim on a statistical basis. In this chapter, we present key components of a formal hypothesis test. There are 8 steps. The concepts are general and apply to hypothesis tests involving lots of different things, but in particular, proportions and means. So these are ways of testing claims about the proportion or the means of a population. Example, average service time of a Taco Bell Defy is less than 2 minutes. It's a claim on the population. The average of all service times is less than 2 minutes. On the proportion side, more than 85% of Americans own a smartphone. That is a claim about all Americans. We're saying that 85% of them have a smartphone. These are claims about population parameters. How do we verify that when all we have is a single sample? Here is an 8-step method for hypothesis testing. Step 1, identify claim. Step 2, negate claim and form alternative claim. Step 3, identify null and alternative hypotheses. Step 4, select significance level. Step 5, identify and compute test statistic. Step 6, find p-value. Step 7, make determination. Step 8, restate decision in non-technical terms. So the decision you made in step 7. All right, we're going to be going through each of those with a bit more elaboration. First, identify the claim you're trying to validate. Then put it in symbolic form. Next, negate that claim. What is the opposite of the original claim? Put that in symbolic form. Step 3, identify null and alternative hypotheses. You have 2 statements, one and its negation. One of those is going to have an equality, and the other one is not going to have an equality. Whichever statement has equality, put that as your H0 statement, your null hypothesis. That's what the H stands for. H1 is the alternative hypothesis. In the homework, you will see this denoted HA, and sometimes it is denoted H capital A. All of those are appropriate. The null hypothesis is almost always labeled H0. Okay, so the null hypothesis gets the statement that has equality in it, and the alternative hypothesis, H1, has the statement without equality. Step 4, select significance level. This is similar to your confidence level for margin of error. We call it alpha. If not specified, we generally pick 0.05. Step 5, identify the test statistic. Now this is another slide I'd very much like to bookmark, because look at all this information it has on it. If your parameter that you're making a statement about is a proportion, use this formula for your test statistic. You've got your sample proportion and your population proportion that is given, P is given by null hypothesis. Given by your null hypothesis, that's what you will plug in for P. Okay, all right. The distribution, and this will make more sense later on, is normally distributed. And so that's what we're going to use to find the p-value later on. This table has more information than you know what to do with at this point. But believe me when I say you will find it helpful later on. If I'm testing a claim about a population mean, I'm going to use this t-statistic here. But that's only when I don't know the standard deviation. When I know the population standard deviation, it becomes normally distributed, and I use this here. Okay, if you were required to approximate a standard deviation or prove a claim about standard deviation, you would use what is called the chi-squared distribution, which we will talk about later on because it's important in goodness of fit tests. You would use this statistic for chi-squared. Don't worry about having to do that this chapter. Step 6, find the p-value. The p-value is the probability of a sample being as extreme or more extreme than data given a null hypothesis. This is related to significance. Is our data significant or not? Okay, so there's 3 different situations. See, so your null hypothesis has the equality. The alternative hypothesis is going to have the other possibility. There are 3 of them. It could be not equal, less than, or greater than. If it's not equal, it's a two-tailed test. The p-value represents twice the area of the tail beyond the test statistic. If it is a left-tailed test, then the p-value is the area to the left of the t-statistic. If it is a right-tailed test, then the p-value is the area to the right of the statistic. That is a right-tailed test, and that happens when the alternative hypothesis is greater than or equal to. And what's going on here is we have this distribution, either normal or t distribution, and then we have our test statistic, which is either t or z, depending on the distribution. If it is a right-tailed test, we want this area here, what the p-value will be. That is if it is a right-tailed test. All right. Okay. So, again, just keep that in mind. It'll make more sense when we do an example. Okay, step 7, make a determination. Is the p-value less than alpha? If yes, your data is extreme. If the p-value is less than alpha, then that data is regarded as extreme under the assumption of the null hypothesis. We reject the null hypothesis. If the p-value is bigger than alpha, then your normal everyday data is not so extreme, even when we assume our null hypothesis, which we're trying to either reject or otherwise. So the null hypothesis may be reasonable. We fail to reject the null hypothesis. All right, but that's step 7, make that determination. Step 8 is the final step. Restate the decision in non-technical terms. Restate according to the original claim, which will abbreviate OC. Here are examples. So if you reject the null and the original claim is in the alternative hypothesis, say there is sufficient evidence. If you reject the null, state the the original claim. If the original claim was H0, was the null hypothesis, then it's the original claim you want to state your conclusion with respect to. You say there is sufficient evidence to reject. I left out the word evidence there. If you fail to reject the null and the original claim was the alternative hypothesis, then you don't have enough information to support the alternative hypothesis. If the original claim was your null hypothesis and you failed to reject it, then you'd say there's not enough evidence to reject that original claim. We're going to go over this in the context of an example. And with a few more examples, you'll get the hang of it. In a poll of 1,009 customers, 54%, it was actually 545 consumers, responded that they were not comfortable with a drone delivering their purchase. They just don't think that would be a good idea. All right, now the claim that we would like to investigate, and usually the claim is just given to you, but in this case we'll kind of think of it ourselves. The claim to investigate is that the majority of consumers are not comfortable with drones delivering their purchases. Okay, so that's the claim, and we want to test that claim. All right, now, what I'm going to do is open up Excel. Now, we're going to be in Excel a lot this unit. Come up with a title for the problem. Let's get into the steps. Step 1. The original claim, the majority of consumers are not comfortable with drones delivering their purchases. That's our original claim. All right, what's step 2 now? We want to write this claim in symbolic notation. We're talking about a majority of customers. Well, a majority is more than 50%. That's a proportion. And so this original claim is that if we let P be the proportion of customers not comfortable with drone deliveries, then our claim in symbolic notation is P is greater than 0.5. I'm using P rather than P hat because this is a population parameter. All right, step 2. What is the negation of that? What's the opposite of that? That's going to be P less than or equal to 0.5. It's the opposite of greater than. It's going to be less than or equal to. That's already in symbolic notation. Step 3 is to determine, let me just take a look at these, put these slides side by side. Okay, split view. Great, all right. First, identify the claim. Second, negate the claim. Then put in symbolic notation. We did that. Step 3 is to identify the null and alternative hypothesis. So H0, my null hypothesis, now that's going to be the one that has equality. I'm going to put P equals 0.5. That was my negation here, because that was the one that had equal sign. The alternative then is going to be the other one. So that's going to be P greater than 0.5. So there's my null hypothesis, which I take from my original claim or the negation, whichever has equality. The other one goes into the alternative hypothesis. So the original claim could be in either the null or the alternative hypothesis. Step 4 is to select significance level. In this example, no significance level was given, so I'm going to use 0.05. Alpha is 0.05. Step 5 is to identify and compute the test statistic. So I am dealing with a proportion. It's the proportion P that I'm trying to decide a claim about. N equals 1009. That is from the original statement. P hat is 545 divided by 1009. My test statistic is this thing right here. Z, the normal distribution, Z equals P hat minus P over the square root of P Q over N. Okay, now we are assuming P is 0.5. That is what the P is. So P times N is 504.5, and that's bigger than 5. Let me just write that out. There's my N, and P from the null, and that is bigger than 5. Q also equals 0.05. So NQ is also bigger than 5. We're fine using this. All right, so let's carry on. Q hat is going to equal 1 minus P hat. Enter. 1 minus P hat. Okay, what else do I need? I have P equals 0.5. Q equals 1 minus P. With all that information, I can do my test statistic. Z equals, and this is my test statistic, P hat minus P divided by square root P times Q divided by N. Close the square root. That's it. Let's take a look at that. I'll enter. There's my test statistic. And that's step 5. Let's go to step 6. Find the p-value. I've got my test statistic based on the context. Now, I need to find the p-value. I need to look at what sort of a hypothesis test I'm doing. Is it two-tailed, left-tailed, or right-tailed? What sign is being used in my alternative hypothesis? Is it not equals to? The alternative hypothesis is right here. Is it not equal to, less than, or greater than? Well, it's greater than. So this is a right-tailed test. The p-value is the area to the right of the test statistic, and the test statistic is normally distributed. We can see that right here, normally distributed. All right, so p-val equals, okay, now it's area to the right I'm looking for. So I'm going to go 1 minus norm dist, my test statistic, comma, it's a z-score. What's the mean and standard deviation of a z-score? Mean is 0, standard deviation 1. Because its area cumulative is 1. Close parentheses, enter. There's my p-value. So look at that again. 1 minus norm is going to give me, the norm.dist is going to give me values, area to the left of my test statistic, which is 2.55 standard deviations above the mean. That norm.dist value is really big. It's the area on the left, but I want the area on the right. So I'm going to subtract from 1 the area on the left to get the area on the right. And I get 0.0053. Okay, I found my p-value. Now it's time to go to step 7 and make my determination. Is the p-value less than alpha? Yes, so I reject the null hypothesis. I reject the null hypothesis. The p-value is the probability of finding data as extreme or more extreme than my sample. That probability is very small. And so what that means is that my normal little old sample is really, really extreme. But why is it extreme? It's extreme assuming the true population proportion is 0.5. I'm going to say that assumption doesn't work. That's a bad assumption because my data should not be unusual, should not be significant. It's just normal data. All right, and so that's how that works. So I reject the null hypothesis. And so why don't I go ahead and write that? Reject the null. Step 8 now is to rephrase your conclusion with regard to the original claim. The original claim was that the majority of people were comfortable or were not comfortable with drone deliveries. Okay, and so the null hypothesis that the proportion of people who are comfortable is 50%, there is evidence to support the claim that the majority of consumers are not comfortable with drone deliveries. Great, so there's my solution. All 8 steps. I want you to answer these questions. Just go ahead and write them on this slide. So again, Taco Bell's 2-story neon purple lit Defy restaurant is going to be, as they arrived with a bold objective to get customers through the drive-thru in 2 minutes or less. How do you know if this is achieved? Given a sample of 25 service times. The data here is in seconds. All right, I'm going to grab the data. I'm going to go to Notability Canvas, the home page. I see the Taco Bell Defy XL. I'm going to go ahead and click on that. I'm going to share it to Excel. Let's see, do I want to delete this draft? Yeah, delete it. Okay, here's our service times. Great, now I want to go to Notability. All right, I need to do a hypothesis test. The null hypothesis here is going to be, so let me go ahead and put this in. So first thing I'll do is I'm going to insert a column, click there, copy, save a copy. Now I can insert. All right, I'm just going to let my data hang out there on the side, and I'm going to put my steps here. So step 1. First is identify original claim. And so the original claim is going to be the mean service times are less than 2 minutes. So mu is the population mean. Mu is less than 2 minutes. I'm going to put everything in seconds because all my data is in seconds. So I'm going to do 120 seconds. So mu is less than 120. Step 2, what's the opposite of that? Well, the opposite is mu greater than or equal to 120. There it is, written in symbolic notation. Step 3 is to determine my null and alternative hypothesis. I'm going to go H0 colon, see what is that going to be. Which one has equality? The negation has equality. This one has equality. I'm going to write mu equals, remember the null hypothesis has to be equality. Mu equals 120. The alternative hypothesis, H8, is my original claim. Mu is less than 120. Great, I've got my null and alternative hypothesis. Step 4 is now to, let me just go back here, significance level. Again, the significance level is not specified, so I'm going to use alpha equals, what? 0.05. Okay, now for step 5. Identify test statistic. What situation am I dealing with here? It's not a proportion. It's a mean, right? The mean service time. Is the population standard deviation known? No, they didn't give me any population standard deviation. That was not suggested at all. There's no population standard deviation, so I cannot use that second row. I have to use, oh, no, forgive me. I can't use the one where sigma is known. I'm going to use this one where sigma is not known. My standard deviation is not known, and so this is a t distribution. I need to use this test statistic, this one right here. There's a number of things I need. We need p hat and x bar. X bar equals the average, so I'm going to select these, equals average there, and put that, enter. There's my x bar. I need mu, but I know what that is. Mu has got to be 120. I need s equals stdev dot s, because it is a sample. I'll go down like that, enter. So there's s, and the last thing I need is just n. N equals 25. Okay, and so now it's time for me to do my test statistic. T equals x bar minus the mean divided by s divided by square root n. Press enter. And there's my test statistic. That concludes step 5. Now for step. Okay, let's find the p-value. Because the null hypothesis has less than in it, it's a left tail test, degrees of freedom. That's something I need before I do my p-value. Degrees of freedom is going to equal n minus 1. Enter. Okay, and so now we can find the p-value. P-value equals t dot dist. Look at this, it's got two-tailed, right-tailed, or just t dot dist. So I'm going to put t dot dist. It says x, I'll put that. And then it wants degrees of freedom. I'll put that right there. and then cumulative, I'll put 1 because I want the area. Press enter. There is my p-value. So step 7. Now I make my determination. Is the p-value smaller than alpha? The answer is no. So we fail to reject the null hypothesis. Great. Step 8 is to rewrite our conclusion. We're going to say there is not sufficient evidence to support the claim that the average service time is less than 2 minutes. We certainly can't claim that with the data we have now. There's that example. All right, here's a few more questions for you to answer. Now I want to talk about type 1 and type 2 errors. A type 1 error is rejecting the null hypothesis when it is in fact true. The symbol alpha is used to represent the probability of a type 1 error. So that's how our significance level and our outcome of the hypothesis test are related. Alpha is the probability of rejecting H0 when H0 is true. Whether we reject H0 or not is based off of the sample that we have. And that data sample is regarded as a random variable. Type 2 error is the mistake of failing to reject the null hypothesis when it is actually false. So, yeah, the symbol beta is used to represent that probability. Here's a little table and a mnemonic. The true state of nature here is that's the columns. So the first column is that the null hypothesis is true. The second column is if the null hypothesis is false. If we reject the null when the null hypothesis is true, then that is a type 1 error. If we reject it when it's false, that's the correct decision. If we fail to reject it when it's true, that's the correct decision. But if we fail to reject it when it is false, that's a type 2 error. Mnemonic to remember, RTN's for reject true null, type 1. That's the first one. And then FRFN, reject, fail to reject false null. That's the second. That's type 2. Okay, so let's take this example. We'll consider the claim that a medical procedure designed to increase the likelihood of a baby girl is effective. So the probability of a baby girl is p greater than 0.5. Give the following null and alternative hypotheses. Write statements describing a type 1 and a type 2 error. Okay, given, here's our hypotheses. The original claim that will be addressed is the final conclusion, right? Okay, so type 1 error, which is going to be, so the type 1 error is going to, well, it's going to be, what do? We reject true null in a type 1 error. So the null is true, and we reject it. So what we do is we support p equals 0.5 when p actually does equal 0.5. Type 2, a type 2 error would be we failed to support p greater than 0 when it was actually true. P was greater than or equal to 0.5. And we failed to support that because the sample didn't support it. Great. So I'm going to go over 4 examples of hypothesis testing. You're welcome to continue watching, but you don't have to. For those ending it here, I'll see you in class. And for those of you who carry on, let's get started. Okay, so you've got the drug OxyContin, which is OxyContin, is used to treat pain, but it's dangerous because it is addictive and can be lethal. In clinical trials, 227 subjects were treated with OxyContin and 52 developed nausea based on data from Purdue Pharma LP. Use a 0.05 significance level to test the claim that more than 20% of OxyContin users develop nausea. Does the rate of nausea appear to be too high? All right, for that, let's go to our Excel sheet. This is example 1. Use the 0.05 significance level to test the claim that more than 20% of OxyContin users develop nausea. The original claim is more than 20% of users develop nausea. What is that in terms of notation? Let P be the proportion of users that were nauseated. All right, and the idea is that the claim is that more than 20% did that. So that would mean that P is greater than 0.20. All right, my original claim. Step 2 is the negation. That's P is less than or equal to 0.2. Step 3, that's already in notation. Step 3 is the hypotheses. So H is going to be the one that has equality. The null hypothesis always has equality. So P equals 0.2. And the alternative hypothesis is P is greater than 0.2. This one did not have equality. My original claim is in the alternative hypothesis. Whoops, I did step 3 twice. This is step 2 twice. Okay, there. All right, now, step 4. And what is step 4? Step 4 is select confidence level, and step 5 is test statistic. So the confidence level is alpha equals 0.05, given in the problem. Step 5, the test statistic. What test statistic am I going to use? This is a proportion. The test statistic is z distributed, and it's p hat minus p over square root pq over n. That's my test statistic. I could look that up on the sheet to make sure. Yeah, there it is. So I'm going to start getting everything I need. I need p hat. P hat equals the data, okay, equals 52 divided by 227. Enter. Actually, the next thing I need, I'll just do P. P is, because of the null hypothesis, P is 0.2. Enter. Now I need Q equals 1 minus P. There it is. Now I need N. N equals 227. All right. Now my Z statistic, or my test statistic, Z equals this thing, equals parenthesis P hat minus P, close parenthesis, divided by square root P times Q divided by N. Enter. 1.095. That's my test statistic. Step 6 is to compute the p-value. Normally distributed. Here's 0. Here's 1.09. I need to find the alternative greater than. So I'm looking for this area about 1 standard deviation away. That area is not very small. Let's do this now. Equals the area to the right, 1 minus norm dot dist. X is my z value. Mean is 0. Standard deviation is 1. Cumulative is 1. Enter. And I get 1.13. Okay. And this thing, I'll just go ahead and make a note. This thing is bigger than alpha. So step 7 then, I'm going to make my determination. And my determination will be to fail to reject the null. I'm doing that because P is not less than alpha. If P were less than alpha, then my data would be extreme given the null hypothesis. But it's not really extreme, so my null hypothesis is not far-fetched. I'm not going to reject it. Step 8, write the original claim. There is not sufficient evidence to suggest that 20% of users become nauseated. I should change this to more than. There is not evidence to suggest that more than 20% of users become nauseated. There's just not enough evidence to suggest that. The data we had was over 20%, but it was close enough for it not to say the actual proportion is equal to 20%. Great, let's go on to the next example. Example 2. Let's see, there it is, sheet 2. This example is the garlic. Garlic and... In a test of the effectiveness of garlic in lowering cholesterol, 49 subjects were treated with raw garlic. Cholesterol levels were measured before and after treatment. The changes in their levels of LDL cholesterol have a mean of 0.4 and a standard deviation of 21. Use the 0.5 significance level to test the claim that with garlic treatment, the mean change in LDL cholesterol is greater than 0. But what do the results suggest about the effectiveness of the garlic treatment? The original claim is that the mean change is greater than 0. In symbolic notation, this is going to be mu. Mu is greater than 0. That's our original claim in symbolic notation. The negation of that is mu is less than or equal to 0. The null hypothesis is H naught is mu equals 0, and the alternative hypothesis is mu is greater than 0. So the equality one had to go into my null hypothesis, and I took away the equal sign. The null hypothesis always has to be equal. The other one went into my alternative hypothesis. Okay, so there's my hypotheses. Step 4 is going to be significance level. This time it is given to be 0.05. Step 5 is to identify and compute the test statistic. No sample standard deviation is present. Let's see. So we're going to use the one from the second row of that table. It's about the mean, and there's no standard deviation. M is greater than 30. N in this case is 61 or something. N in this case is 49. All right. So the test statistic we are going to use is T equals X bar minus mu over S over square root N. We need X bar equals, see, they give us X bar. The mean is 0.4, enter. Now we need mu. Mu, according to the null hypothesis, is 0. We assume the null hypothesis, so mu is 0. We need S, standard deviation of a sample. I don't need that because it gives me the standard deviation equals 21.0. All right. N equals 49. Now we can compute our T statistics. T equals X bar minus mu divided by 21 divided by square root. All right, take a look, 0.3133. Step 5. Now step 6, we need to find the p-value. P-val equals, is this a right-tailed, left-tailed, or two-tailed test? Because the alternative hypothesis is greater than, this is a right-tailed test. If it were less than, it'd be left. So I'm going to do T dist, and notice there's this command T dist RT, which stands for right-tailed. I'm going to select that, put in my T statistic, and degrees of freedom, N minus 1. Enter. 0.447, which is bigger than alpha. So step 7, fail to reject null. It's because the p-value is much bigger than alpha. Conclusion: I failed to reject the null. Not sufficient evidence. My conclusion: not sufficient evidence to suggest the mean difference is negative. All right, go on to the next one. This is example 3 about tennis instant replay. The Hawkeye electronic system is used in tennis for displaying an instant replay that shows whether a ball is in bounds or out of bounds. Players can challenge calls made by referees. In a recent U.S. Open, singles players in 97 challenges and 231 were successful with the call overturned. Use a 0.01 significance level to test the claim that fewer than 1/3 of the challenges are successful. What do the results suggest about the ability of players to see calls better than the referees? All right, let's do this. So step 1, the original claim. The original claim is fewer than 1/3 of challenges are successful. What is that in symbolic notation? Let's see. So let P be the proportion of success calls. So step 2 is going to be, oh wait, I didn't finish. Okay, and so the claim is P, the number of challenges, is less than 1/3. Step 2. You know what would be a good idea is if you pause this video and did as much as you can, and then check if it's right. Step 2 now is the negation. The negation is P is greater than or equal to 1/3. Step 3 is the hypothesis. The null hypothesis has equality, the negation of the original claim. So that's P equals 1/3. The alternative hypothesis, P is less than 1/3, which is the original claim. Step 4 is the level of significance, 0.01. Now it's time for the test statistic. This is a proportion, so it's the Z1. Z equals P. It's going to be P hat over P over square root P Q over N. All right, so what do I need? I need P hat. P hat is given 271 divided by 879. And then, what do I need? I need P bar. Let me get rid of that. Okay, I need P. P is equal to 1/3. I need Q. Q is 1 minus P. I need N. N is 879. Let me check P hat. Yeah, 879. All right, great. That's all there. So now I'm going to do Z equals, and I just plug everything into that formula. P hat minus P divided by square root of P times Q divided by N. Okay, there it is. It's negative. All right, now step 6. I need to find the p-value. So p-val is going to equal, all right, now I need to think, what kind of a test is this? This is going to be a left-tailed test. Less than, left-tailed. I want the area to the left of my test statistic. Excel gives me anyway, so I'm going to do norm.dist, press tab so that it fills in everything for me. Z, this is a Z normally distributed. 1, standard normal distribution. Enter. You need to see the Z-score again. There's the Z-score. There's the P. Now step 7. Make our determination here. Step 7, what do? We fail to reject or reject the null? In this case, we're going to fail to reject because P is bigger than alpha. Step 8, there is not sufficient evidence to support the claim that less than 1/3 of claims are successful. Indeed, it seems like this would suggest that more than 1/3 of the claims are successful. All right. 1 in every 3 claims at least is successful. All right, let's do the last example. Example 4, diet. Step 1, original claim. Now would be a good time to do this and see what you get. When 40 people use the Weight Watchers diet for 1 year, their mean weight loss was 3 pounds, and the standard deviation was 4.9 pounds. Use a 0.01 significance level to test the claim that the mean weight loss is greater than 0. Based on these results, does the diet appear to have statistical significance? Does the weight loss appear to have practical significance? Okay, so the claim here, which they pretty much gave us, test the claim that the mean weight loss is greater than 0. Mean weight loss is greater than 0. So mu is greater than 0. The negation is mu is less than or equal to 0. That is the one that has the equality in it. You know what? Why don't we mix things up just a little bit and change this? Let's say that the original claim, let me modify this. Let's say that the original, well, no, this is not good for people who've already started. Let's carry on. The original claim is that, so there's my alternative. Now I need to come up with my hypotheses. H0, mu is equal to 0. H1 is mu is greater than 0. A right-tailed test. Significance level is 0.01. Now, step 5, test statistic. This is a mean where we don't have a population standard deviation, so it's t distributed. The test statistic is going to be t equals x bar minus mu over s over square root n. That's the test statistic in this case. Let's do this. I need x bar. Their mean weight loss was 3 pounds. Do I need to make that negative? The original claim is about loss. That's going to be 3. Now I need mu. Mu equals 0. The standard deviation is 4.9 pounds. And n equals 40. Now we've got, so t, we've got x, c equals x bar minus mu, which is 0, divided by s, divided by square root n. Close that. Step 6 now is to compute the p-value. That is going to equal my t, this is a t distribution, equals t dist, right-tailed because it's greater than in my alternative hypothesis. There's my t statistic, and degrees of freedom is n minus 1. That is less than alpha, 0.01. Step 7 is I'm going to reject the null. Step 8, my conclusion is there is sufficient evidence to support the claim that there is sufficient evidence the mean weight loss was greater than 0. That's my last example, so that's it.